Dear students, in our previous videos we discussed about semiconductors. Now let us move on to next class of materials, namely dielectrics. This is the outline of the syllabus. First we will start with fundamentals, where we need to discuss something about historical background, dipole, the concept of dipole and dipole moment. Next, dielectrics and types of dielectrics, namely polar type and non-polar types. Coming to basic terminologies which we use in dielectrics, that is polarization, polarizability, susceptibility, and the three fundamental vectors, few basic equations and relations. Next is Clausius-Moussetti equation. Here we have to discuss types of polarization and internal field, Lorentz field, and derivation of Clausius-Moussetti equation. Finally, we end up this chapter by discussing applications, where we need to discuss about types of dielectrics, applications, and one particular application, that is role of dielectrics in transformer. History of dielectrics. Leyden jar, an antique electrical component which stores a high voltage electric charge, was discovered by Dutch scientist Peter van Musschenbroek of Leyden in 1745. It was the first means of accumulating and preserving electric charge in large quantities. You can treat Leyden jar as equivalent to a capacitor. Experiments of Benjamin Wilson and Benjamin Franklin in 1749 reported that a thinner layer of dielectric material enhances the charge accumulation. Perhaps this is the first time when a dielectric material was used in capacitor. In 1837, Faraday repeated the experiments of Cavendish, showing that when a space between the plates of a capacitor is completely filled with insulating material such as glass, mica, paper, etc., the capacitance increased by a factor K, called dielectric constant. The term dielectric was coined by William Whewell in response to a request from Michael Faraday. This is the first Leyden jar. This is Benjamin Franklin and Michael Faraday. Now we will see some comparison between conductors, insulators, and dielectrics. See, the materials are classified into conductors, insulators, dielectrics, semiconductors based upon their ability to conduct electricity. We already discussed about semiconductors in previous videos. Now we will go ahead with the discussion of dielectrics. Here is the comparison. Conductors. As we all know, they conduct electricity easily. They feel the applied electric field but does not affect it. That means when you apply electric field to a good conductor, there will be no change either in the magnitude or in the direction of the applied field. And all conductors consist of free charge carriers, which are also called as free electrons or conduction electrons. And these electrons run away from each other as fast as they can. All metals are good conductors. Next, insulators. First of all, they does not conduct electricity. Next, they does not feel the applied electric field, and hence no change in the applied field. So, when you apply electric field to a good insulator, there will be no effect of the electric field on the insulator at all. Life is much more restrictive for electrons. That means electrons are not free. They are not at all free to move. Glass, ceramics, diamond, air, etc. are insulators. Now coming to the main topic, that is dielectric. Dielectrics, all dielectrics are insulators. Hence they don't conduct electricity. When placed in the external field, they interact and reduce the net field. This is a major difference between dielectrics and insulators. As I told few seconds back, insulators does not feel the applied electric field, but dielectrics, they feel the applied electric field, interact with the applied electric field, and reduces the magnitude of the field. Why? We will discuss later on. Dielectrics are made up of dipoles, so they consist dipoles. Dipoles are not free, means they are not as good as free electrons. They are not free to move, but they can rotate about their axis. Water, paper, quartz, silicon oil, carbon dioxide, inert gases, etc. are dielectrics. See this. I said all dielectrics are insulators because there are no free electrons. But all insulators are not at all dielectrics because they do not contain dipoles. Hence, they need not be dielectric. So, we can say all dielectrics are insulators, but all insulators are not dielectrics. Now, we will discuss dipole and dipole moment. Dipole is a combination of two equal and opposite electric charges separated by a very small distance. The distance is in terms of nanometer. The size or strength of a dipole is measured in terms of dipole moment. It is defined as the product of magnitude of any one charge and the distance of separation between them, and it is given by mu equals 2aq into a cap. This is one typical dipole which consists of negative charge of magnitude minus q and positive charge same magnitude but plus q. And this is the distance of separation. The line joining these two charges will be termed as axis of the dipole, and all measurements are made with respect to center of the axis. Look at this arrow mark. It represents direction of the dipole moment. Dipole moment is always directed towards the positive charge. Dipole exists at atomic and molecular level due to unequal sharing of electrons. Dipole concept is used to model many real-world systems including atomic and molecular interactions. What is this atomic and molecular level? Let me take one example. That is example of sodium chloride molecule. It consists of Na plus, that is positive charge, Cl minus, that is negative charge, separated by a small distance. So it is nothing but a dipole. So this is the dipole at molecular level. Similarly, we can have dipole at atomic level also. Well, dielectrics are a class of materials containing dipoles and able to affect the applied electric field. We have not touched this particular part yet. We will discuss it in detail. An important application of dielectric is to separate the plates of a capacitor. Molecules of dielectrics are of two types, namely polar and nonpolar. In polar type, the effective center of positive charge and negative charge do not coincide and there exists individual dipole moment. Example, water, NaCl, HCl, etc. So, this is a polar type molecule. Next is nonpolar. In nonpolar type, effective centers of both positive and negative charges coincide and hence dipole moment is zero. Example, oxygen, hydrogen, carbon dioxide, inert gases, etc. See, by and large, all linear molecules are nonpolar type and all non-linear molecules are polar type. So, linear structures non-polar type, non-linear structures polar type. Polarization, an important term which we frequently use in this chapter. What is polarization? See, in the absence of external electric field, dipoles are randomly oriented within the dielectric slab and the net dipole moment is zero. This is the scenario inside the dielectric. These are the dipoles. All the dipoles are randomly oriented and the total dipole moment is zero. When you apply external electric field to this slab, dipoles rotate in the direction of the field and net dipole moment increases. So this is what is going to happen. This is the direction of the applied electric field and these are the dipoles. See, all the dipoles are aligned in the direction of the applied electric field. This process is known as polarization. Here is another illustration. Next, due to polarization, negative charges are developed on one surface and positive charges on the opposite surface of the slab. Look at the dotted line over here. Dotted lines represent dielectric slab. This face of the slab acquires net positive charge. This side of the slab acquires net negative charge. These charges are known as induced charges. Remember, in the whole scenario, we have two types of charges. First type, charges deposited on the plates of a parallel plate capacitor. Here we have positive charge, which is clearly visible in this diagram. So these charges are also called as free charges. So here it is positive charge, here it is negative charge. Second type of charge is induced charge. Induced charges appear only on the faces of the dielectric slab. So here we have positive induced charge, here we have negative induced charge. Now comes the mathematical definition of polarization. Polarization is defined as the net dipole moment per unit volume, that is mu divided by V, where V stands for volume of the slab. Polarization depends mainly on two terms, which are applied electric field and number of atoms or molecules per unit volume. The polarization is directly proportional to applied field. If E is the applied field, N is the number of molecules per unit volume, then P proportional to E. As E increases, means when the applied electric field increases, polarization also increases, means dipoles rotate more and more and they align in the direction of the applied field. So P proportional to E, which can be written as alpha into E, or we can also write it as P is equal to N into alpha E, where N stands for number of molecules per unit volume. Here alpha is known as polarizability. It is defined as the ratio of polarization to the applied electric field, and it is given by alpha equals P divided by E. To be precise, E in this equation is local field at the site of individual atom or individual dipole. That means we take only individual dipole while defining alpha. That means alpha is treated as a microscopic parameter. There is one more way of defining polarization. Polarization at macroscopic level is also given by equation P equals epsilon naught chi into E, where this symbol chi is known as dielectric susceptibility. What it is? It is a measure of easiness with which dipoles rotate or orient themselves. Higher the value of chi, more easily polarization occurs. That means chi is a macroscopic phenomena and it is given by this equation, that is chi is equal to P divided by epsilon naught into E. Susceptibility depends upon crystal structure of the material and of course temperature, means how easily these dipoles rotate when field applied depends upon the atmosphere around each and every dipole, which is nothing but crystal structure, and of course temperature of the whole slab. If temperature increases, the orientation rate decreases, means dipoles cannot orient so easily, so susceptibility decreases. So we can say susceptibility is inversely proportional to temperature. And finally we can say there is one major difference between alpha and susceptibility. Alpha, that is polarizability, is a microscopic phenomena, and chi, susceptibility, is a macroscopic phenomena. In dielectrics, we frequently talk about three field vectors. They are displacement vector represented by D, polarization vector represented by P, and electric field vector represented by E. We already discussed polarization P and electric field vector, that is E. What is this displacement vector? It is simply equal to flux density and it is given by D equals epsilon naught into E, and this equation is borrowed from electrostatics. If there is any dielectric medium in the given vicinity, then flux density or displacement vector can be written as epsilon r into E, where epsilon r is also known as relative permittivity or dielectric constant. When there is no dielectric between the plates of a parallel plate capacitor, only free charge Q appears on the plates. When dielectric is inserted, charges are induced, and induced charges Qi, which I mentioned in the previous slide, appear on the inner faces of the dielectric, like this. This is the scenario when there is no dielectric and we have free charge of magnitude Q. When you introduce dielectric slab, due to polarization, there arises what is known as induced charge of magnitude Qi. Now comes a new definition for displacement vector and polarization. Displacement vector is a ratio of free charge and the area of the plate, and polarization is a ratio of induced charges and surface area of the dielectric slab. Now we will derive a relation connecting three fundamental vectors, that is D, E and P. Consider a dielectric slab placed between the plates of a parallel plate capacitor like this. Let EA be the applied electric field, this is applied electric field, and E dash be the internal field developed due to induced charges. See what happens here. When you apply electric field, as I told in the previous slide, charges are induced within the slab. As a result, a new field is induced, that is called induced field, also sometimes called as internal field. And look at the direction of these two fields, they are quite opposite. These two are opposite in direction, hence the resultant field is E equals EA minus EA dash. EA, that is the field between two parallel plates, we already know that sigma divided by epsilon naught. Sigma is nothing but charge divided by area, therefore it is Q divided by epsilon naught into A. Dear students, try to recall this equation which you might have derived in second PUC using Gauss theorem. Minus E dash. In the same line, we can write E dash as Qi divided by epsilon naught into A. But in the previous slide, I defined D as Q divided by A. Therefore, this equation becomes D by epsilon naught and this becomes P by epsilon naught. Next, you take 1 by epsilon common factor, we have D minus P. So, E is equal to 1 upon epsilon naught into D minus P. Cross multiply, epsilon naught goes here and shift minus P this side. So, we end up with the equation D equals epsilon naught E plus P. Further, D, I recall this equation, epsilon naught E plus P. Put D which is equal to epsilon naught E. Then, this equation becomes epsilon naught E equals epsilon naught E plus P. Rearrange the terms, then P equals epsilon naught E minus epsilon naught E. Take epsilon naught common factor, we have epsilon naught minus 1 into E. But we know P is given by epsilon naught chi into E. So when you compare these two equations, P, epsilon naught, E. So a chi must be epsilon r minus 1. So chi is equal to epsilon r minus 1. Coming to the last part of this discussion, directions of three vectors. D is related to charges stored on the plates of the capacitors. P is related to bound charges or induced charges. That means D comes into picture only when there is no material medium between the two plates of the capacitor. P comes into picture only when there is a material medium like dielectric between the plates of the capacitor. But E is connected to both free charges and bound charges. And here is the diagram. In this region, there is no dielectric slab and these arrow marks represent displacement vector. In this region, we have dielectric material. So these arrow marks represent polarization vector and these arrow marks represent electric field vector. Look at the electric field vector. It is the combination of free charges as well as induced charges. Now coming to two main definitions which are connected to dielectric material. The two important terms associated with dielectric material are dielectric constant and dielectric strength. Dielectric constant, the ratio of permittivity of a material to the permittivity of free space is known as dielectric constant or relative permittivity. The second one, the minimum applied electric field at which dipole breaks up and dielectric loses its property is known as dielectric strength. See, when you increase the electric field, dipoles, they may break up because of the attraction between these two and attraction between these two. So, the charges are pulled towards the plates of the capacitor and finally the dipole will break up. Once the dipole breaks up, these charges become free and dielectric finally converts into conductor. So, it is no more a dielectric. For example, air loses its dielectric property at an electric field of 3 into 10 power 6 volt per centimeter. I hope you studied these things already in your PUC classes. So that's why I am just giving only the definitions of dielectric constant and dielectric strength. And this is the equation for dielectric constant, that is epsilon divided by epsilon naught. Dear students, I end up my first video on dielectrics now, and the second video you have to watch after thoroughly understanding this video. Thanks for watching the video.